This animated scatter plot shows a familiar rule of real estate. Bigger houses generally cost more money. We measure the house size on the horizontal axis, the price on the vertical axis, and draw a street prediction line right through the middle of our local neighborhood data. But the real world is messy. Look closely and you'll see almost no actual house price sits exactly on that perfect mathematical line. Some sell for a little more than expected, and some for a little less. We call that vertical gap between what the line predicted and what the house actually sold for a residual. Those gaps are the mathematical leftovers of our model. They are the exact measurements of where our algorithm guessed wrong. Drawing a straight line through data is the easy part. The real work, and the only way to prove you can actually trust that prediction, is putting those leftover mistakes under a microscope. To analyze these mistakes properly, we first have to put them all on the exact same scale. It is similar to converting a dozen different foreign currencies into a single uniform currency so they can finally be compared. This textbook formula shows us how to achieve that uniform scale. It calculates what we call a standardized residual. Putting the leftovers on a uniform scale allows us to instantly spot the hidden, extreme weirdos in our data pool. This scatter plot shows what happens when we encounter extremes. Imagine an average-sized house sells for $10 million because it was secretly owned by a rock star. That massive vertical gap breaks the expected pattern completely. In statistics, we call this an outlier. Without standardizing our residuals, these extreme vertical outliers would quietly skew our confidence. Now they are exposed and can be managed. Vertical mistakes are one challenge, but we also have to watch out for a different problem: extreme horizontal data points. Imagine a developer builds a sprawling 50,000 square foot mega mansion right on the far edge of our normal everyday suburban town. Because this house's size is so incredibly extreme, the math grants it massive pulling power. We call this horizontal phenomenon high leverage. It acts like a gravitational black hole, dragging the prediction line away from the normal houses. So how does a data scientist measure if this horizontal leverage is actually ruining the model for everyone else? This equation outlines a vanish test, officially known as Cook's distance. You temporarily delete the extreme point, redraw the prediction line without it, and measure the difference. If removing just one castle drastically shifts the prediction for an entire neighborhood, that data point has too much influence and must be flagged. Let's propose a new idea. What if we try to make the predictions smarter by feeding the algorithm another layer of data, like counting the total number of floor tiles in the house? There is a logical trap here. Bigger houses inherently have more floor tiles, meaning these two measurements are just repeating each other. When different inputs echo the exact same information into the model, we call it collinearity. This echo chamber heavily confuses the math. The algorithm can't tell which factor is actually driving the price, leading to wild and unstable predictions. This textbook page displays the tool data scientists use to detect those echoing variables, called the variance inflation factor. The only way to fix a mathematical echo chamber is to identify the redundant twin and kick it out of the model entirely. Generating a clean, trustworthy prediction requires active human intuition to curate the data. You cannot simply put blind trust in a computer's math. This visual summarizes our critical steps. We standardize our residuals to isolate those vertical rock star outliers, and we use Cook's distance to manage the gravitational pull of horizontal, high-leverage castles. Finally, we clear the confusion by silencing echoing variables to cure collinearity. This process of cleaning and validating data is a standard requirement for any model, from the simple neighborhood house pricing we've seen here to the massive systems used for stock market forecasting or weather prediction. Ultimately, the reliability of a prediction line is built on the rigorous investigation of the mistakes it leaves behind.